Okay, imagine this. What if everything you thought you knew, like really knew, about our solar system just shifted? What if a world you'd grown up learning about as a planet was suddenly, well, not a planet anymore, only for it then to turn out to be way more vibrant and complex and dynamic than anyone ever really dreamed?
That's pretty much the story of Pluto, isn't it?
Exactly. And it's this incredible cosmic tale that honestly fundamentally reshaped how we understand our own place in the universe. So today we're setting off on quite an epic journey, right to the very edge of our solar system. We're diving deep into the super cold, really mysterious realms of Pluto and its fascinating neighbors, the other dwarf planets. We're going to unpack, well, pretty much everything we know, from how they were found, some surprising stories there, and the gods and myths they're named after, all the way to the amazing spacecraft that have traveled billions of miles to check them out. And because we love a good what if here, we'll even look way into the future and ask, could humans ever actually visit these places, maybe even live there?
Yeah, and our goal today, it isn't just listing facts, right? It's about really digging into the deeper meaning, understanding how these distant, kind of small worlds didn't just get added to a list, but actually forced us to rethink our whole cosmic map.
Huh?
They really challenge our definitions of what a planet even is. They hint at, well, maybe life existing in the most unexpected corners,
Yeah.
and they make us think hard about our own future out there in space. So yeah, prepare for some truly mind-blowing stuff. And like you said, a lot of very, very cool facts.
Right. For centuries, our solar system seemed so tidy, organized, you know? You had the inner rocky planets, Earth, Mars, Venus, Mercury, then the asteroid belt, that big gap, and then the big guys, the gas giants, Jupiter, Saturn, Uranus, Neptune, and way out at the end there was Pluto. Always the smallest, the furthest, the ninth planet. It felt neat, predictable.
It did. A nice, simple model, but then things started getting complicated. Something happened that just blew that tidy picture apart and forced scientists to, well, reevaluate everything.
And that was the Kuiper Belt, right?
Exactly. The emergence of what we now call the Kuiper Belt. For so long, people just picture this huge empty void beyond Neptune, dark and empty. But as our telescopes got better, as we started looking harder, it became clear this wasn't empty space at all. It was this vast dynamic region, just teeming with countless icy bodies. Billions of them, probably.
Wow.
Yeah. It's basically a third zone of our solar system, like the asteroid belt, but much, much bigger and further out. And it's full of these leftover building blocks from when the planets first formed, billions of years ago. Finding this huge populated frontier totally changed how we saw our solar system's layout. It wasn't just planets and empty space. There was this whole other complex structure out there.
And discovering all that stuff out there really stirred things up, didn't it? Especially for Pluto. Because before 2006, Pluto was, the smallest, maybe a bit of an oddball, but it was definitely in the Planet Club. Number 9. Then the International Astronomical Union, the IAU, they stepped in. They decided to formally define what actually makes a planet, laid out 3 rules.
Right, they drew a line in the cosmic sand, so to speak.
But I bet there was a huge amount of debate about that. Even among scientists, where exactly do you draw that line?
Oh, absolutely. The debate was fierce. It was a real clash of, scientific viewpoints, but also public feeling. People liked Pluto being a planet. But the IAU's goal was scientific clarity. They needed a consistent definition because we were starting to find more and more objects out there, some almost as big as Pluto. So the first rule was pretty simple. An object has to orbit the sun.
Okay, Pluto does that. Check.
Yep. The second rule, it needs to be massive enough for its own gravity to squash it into a nearly round shape. We call that hydrostatic equilibrium.
Right. Basically, it has to be roundish. Pluto's roundish too, isn't it, from the picture?
It is, yeah. It meets that criterion too. But then came the third one. And this was the controversial part, the real sticking point for Pluto. The third rule says a planet must have cleared its orbital neighborhood.
Cleared its neighborhood. What does that actually mean in space terms? Like, it bullied everything else out of the way.
Kinda. It means it has to be gravitationally dominant in its path around the sun. It's either absorbed or flung away most other objects that would share its orbit. Think about Earth's fissure. There aren't any other planet-sized things sharing our path. We cleared our neighborhood.
Okay, so Pluto did
Exactly. Pluto is right in the middle of the Kuiper Belt. It's swimming in a cosmic sea of millions, maybe billions of other icy bodies. Now, it's definitely the biggest fish in that part of the pond. It's the largest known Kuiper Belt object, in fact. But it hasn't cleared its path. It shares its orbital space with all that other stuff.
So it's in the crowd, not above it.
Precisely. So what got reported everywhere as a demotion, which sounds pretty harsh, was really, from a scientific perspective, a necessary clarification. We needed a way to make sense of all these new discoveries in the outer solar system. It wasn't about picking on Pluto.
Okay, so not a demotion, but a clarification.
Exactly. And to handle Pluto and these other big round things being found out there, the IAU created a whole new category, the
Oh.
dwarf planet.
Mm.
So a dwarf planet
Sure.
orbits the sun. Check. Round due to gravity. Check. But has not cleared its orbital neighborhood. That's the key difference. Check.
Got it. So Pluto became the first member of this new club.
The founding member. The archetype, really.
Yeah.
And here's the thing. This category, dwarf planets, is now understood to be the most populous class of planetary bodies in our whole solar system. There are way more dwarf planets than regular planets.
Wow, I never thought of it that way. So it's actually the king of the most common type of planet-like thing.
You could definitely see it that way.
Yeah.
It wasn't losing status so much as gaining a new, really important one, defining a whole new class of worlds. That's a pretty profound shift in perspective.
Okay, let's zoom right in on Pluto itself then, because its discovery, how it first popped into our awareness, that's a fantastic story on its own. It really started with Percival Lowell, right? A famous astronomer, built his own observatory. He predicted a planet X beyond Neptune, thought he saw wobbles in Neptune's orbit caused by something else further out.
He did. Lowell's calculations and his search for Planet X really set the stage. And fun fact, as you hinted, the symbol for Pluto, that PL ligature, it stands for Pluto, but it also subtly honors Percival Lowell's initials.
I love little details like that. But Lowell didn't find it himself, did he?
No, he didn't. The actual discovery came down to the incredibly painstaking, meticulous work of a young astronomer named Clyde Tombaugh. He was just 23, working as an assistant at the Lowell Observatory in Arizona, and his job involved spending hours upon hours, night after night, in this unheated observatory dome, freezing cold, comparing photographic plates.
Comparing plates, how did
Yeah.
that work?
He used a machine called a blink comparator. It would rapidly switch back and forth between images of the same patch of sky taken a few days apart. Stars would stay put, but anything closer, like a planet or asteroid, would appear to jump back and forth against the starry background. It was incredibly tedious work, scanning millions of tiny star images. But on February 18, 1930, Tombaugh spotted a tiny, faint speck that had moved in the constellation Gemini. That was it, Planet X.
Wow, after all that searching, what a moment.
Absolutely monumental. The Lowell Observatory officially announced the discovery on March 13, 1930, and they chose that date deliberately. It was Percival Lowell's birthday and also the anniversary of William Herschel discovering Uranus. A nice bit of astronomical history.
And the naming, that's another charming part of the story. It wasn't named by the scientist, was it?
No, the observatory was flooded with suggestions, apparently thousands from all over the world. But the name that stuck, Pluto, came from an 11-year-old girl in Oxford, England, Venetia Burney.
11 years old?
Yeah.
Seriously?
Seriously. Her grandfather was reading the newspaper article about the discovery aloud at breakfast. Venetia, who was interested in classical mythology, suggested that Pluto, the Roman god of the underworld, would be a fitting name for such a dark, cold, remote world. Her grandfather mentioned it to an astronomy professor friend who passed along to Lowell Observatory, and they loved it. It fit the theme of naming planets after gods, and crucially, it started with PL, honoring Percival Lowell.
That's just brilliant. An 11-year-old girl named a planet, well, a dwarf planet now.
And the mythology behind the name is really interesting, too. Pluto in Roman myth, or Pluton in Greek, is more complex than just being the gloomy king of the dead. Originally, the Greek god was Hades, who was pretty stern. But the name Pluton became more popular, especially in connection with the Eleusinian mysteries.
The Eleusinian mysteries, what were they?
There were these ancient, secret religious rites in Greece, tied very closely to agriculture, the cycles of life, death, and rebirth, planting seeds, harvesting crops. So Pluton wasn't just the ruler of the afterlife. He got conflated with Plautos, who was the Greek god of wealth.
Wealth. How did the god of the underworld get linked to wealth?
Because mineral wealth, gold, silver, gems, comes from underground, right?
Yeah.
And also the seeds for a bountiful harvest come from the earth, the realm Pluto ruled. So he represented this hidden underground source of riches, both mineral and agricultural. In those mysteries, he was also seen as a devoted husband to Persephone. They ruled the underworld together. He's often shown holding a bident that's a two-pronged spear, not a trident like Neptune's.
A bident, like a big fork?
Sort of, but it was actually based on an agricultural tool used for digging or turning soil, again linking back to that idea of earthly abundance. Sometimes he's also shown holding a key, symbolizing his control over the locked gates of the underworld and its hidden treasures. So it's a really rich, multifaceted mythological figure for this distant, mysterious world.
Speaking of mysterious, Pluto's orbit is famously weird, isn't it? It doesn't follow the same neat path as the other major planets.
Not at all. It's highly eccentric, which is just a fancy way of saying it's very oval or egg-shaped, not nearly circular like Earth's orbit. Its eccentricity is about 0.2488, which is quite high.
So what does that mean in practice?
It means its distance from the sun changes dramatically. At its closest point, called perihelion, it gets to about 29.7 astronomical units, or AU, that's 29.7 times Earth's distance from the sun. But at its furthest point, aphelion, it swings way out to 49.3 AU. That's a huge difference in distance.
Wow, nearly twice as far out at its furthest compared to its closest.
Exactly. And here's the really mind-bending part. For about 20 years out of its incredibly long 248-year orbit, Pluto actually ducks inside the orbit of Neptune.
Wait, it crosses Neptune's path. Don't they ever collide?
It seems like they should, right? But they don't. They're in what's called an orbital resonance. For every 3 times Neptune goes around the sun, Pluto goes around exactly twice. This gravitational lockstep keeps him from ever getting too close. But yeah, for 2 decades, out of every 248 years, Pluto is technically closer to the sun than Neptune is.
So the furthest planet wasn't always the furthest.
Precisely. The last time this happened was from 1979 to 1999. It really shows that Pluto plays by a different set of orbital rules out there. It's a fascinating cosmic dance.
Okay, let's try to imagine actually being there, standing on Pluto. What's it like? I'm guessing cold.
Cold is an understatement. We're talking about an estimated average surface temperature of around minus 233 degrees Celsius. That's minus 387 Fahrenheit, or only about 40 Kelvin, just 40 degrees above absolute zero.
Minus 233 C. Okay, yeah. So cold that, as the saying goes, pretty much everything we think of as gas or liquid is frozen solid.
Absolutely. Nitrogen, methane, carbon monoxide gases here on Earth, they form vast plains and glaciers of ice on Pluto. It's a landscape sculpted from frozen volatiles.
What's the surface actually made of then? Just nitrogen ice?
Mostly nitrogen ice, yes. That forms the bulk of the surface we see. But it's mixed with methane ice and carbon monoxide ice. And then there are these complex organic molecules called tholins. They're reddish-brown compounds formed when ultraviolet sunlight hits the methane and nitrogen. That's what gives Pluto some of its distinctive colors, especially that large heart-shaped feature, Sputnik planitia.
And underneath all that exotic ice, what's the bedrock?
Surprisingly, it's water ice. But at those incredibly low temperatures, water ice isn't slippery or brittle like we know it. It becomes incredibly hard and rigid, acting just like rock does here on Earth.
So water ice is the rock of the outer solar system.
Pretty much. It forms the structural foundation, the mountains and crust, beneath the more volatile ices like nitrogen. It's strong enough to support huge geological features. It totally flips our Earth-based intuition about what ice is like.
And even being so far from the sun, so incredibly cold, Pluto still somehow manages to hang on to an atmosphere. A thin one, but still.
It does, yes. A very tenuous atmosphere, mostly nitrogen, like Earth's, but vastly thinner, with traces of methane and carbon monoxide mixed in.
How did we even figure out what it was made of before New Horizons got there? Could we tell from Earth?
We had hints from Earth-based observations watching stars pass behind Pluto's stellar occultations, which suggested an atmosphere. But New Horizons really nailed it down, especially with its ALICE instrument.
ALICE. Okay, how did that work?
ALICE is an ultraviolet imaging spectrograph. As New Horizons flew past Pluto and went into its shadow, it looked back at the sun through Pluto's atmosphere. The instrument measured how much sunlight was absorbed at different ultraviolet wavelengths. Gases in the atmosphere absorb specific wavelengths, creating characteristic dips or absorption lines in the spectrum.
Like a chemical fingerprint.
Exactly. By analyzing those dips, ALICE could identify the gases present nitrogen, methane, carbon monoxide, and even measure their abundance at different altitudes, mapping the atmospheric structure up to over 170 miles above the surface. It's an incredibly sensitive technique.
Okay, and you mentioned earlier the gravity is super low. Like, if I wanted an easy way to lose weight...
Pluto's your place. Though maybe not the most comfortable diet plan. You'd weigh only about 1/15th of your Earth weight.
1/15th? Why so little? I mean, it's small, but...
Well, its mass is tiny compared to Earth, only about 14/55th of Earth's mass. But gravity also depends on distance from the center of mass. Because Pluto is much smaller in diameter, about 5.5 times smaller than Earth, when you're standing on its surface, you're much closer to its center.
Ah, so being closer kind of makes up for some of the low mass?
Exactly. It boosts the gravitational pull you feel relative to its mass alone. So the combination of low mass and small size results in that surface gravity being about 0.07 times Earth's, or roughly 115th. You could jump incredibly high.
All right, let's talk about the mission that completely changed everything we knew about Pluto. New Horizons. This was a journey that took, what, nearly a decade just to get there, an incredible feat.
Truly incredible, spanning billions of miles, years of planning, and pushing technology to its absolute limits. It transformed Pluto from a fuzzy blob in our best telescopes into this stunningly complex, active world.
And the idea for it started quite a while back, didn't it? I heard a story about a phone call.
Yeah, that's a great piece of history. Back in August 1992, a scientist at JPL, Robert Stale, actually called Clyde Tombaugh, Pluto's discoverer, who was 86 at the time. Stale basically asked Tombaugh for permission to visit his planet.
No way. What did Tombaugh say?
Apparently, Tombaugh replied, "I told him he was welcome to it, though he's got to go one long, cold trip." Isn't that fantastic? The discoverer giving his blessing. It really puts a human face on these huge endeavors.
That's amazing. But getting from a phone call to an actual launch, that must have taken some serious effort and dedication.
Immense effort. Stamatio's Tom Cremigas at the Applied Physics Laboratory, APL, and Alan Stern were key figures. They formed the New Horizons team around December 2000. Alan Stern especially had been championing a mission to Pluto for years, basically his whole career. Cremigas called him the personification of the Pluto mission. Stern's earlier concept, called Pluto 350, formed the basis for New Horizons. It took incredible persistence to get it approved and funded.
It wasn't the only proposal either, was it? There was competition.
Right. NASA put out a call, and New Horizons was chosen as one of 2 finalists for a concept study, competing against another proposal called PIASI. But APL, proposing New Horizons, had a strong track record. They had recently built and flown the near Shoemaker spacecraft, which successfully orbited and even landed on the asteroid Eris. That really demonstrated their capability for these kinds of complex deep space missions, which likely gave them an edge.
Okay, building the spacecraft itself. Flying almost 4 billion miles from the sun means that sunlight is incredibly faint. Solar panels are basically useless out there, right? So how do you power something for decades in deep space?
That's the critical challenge for outer planet missions. You need a radioisotope thermoelectric generator, or RTG. It's essentially a nuclear battery. New Horizons uses one RTG. Inside, it has pellets of plutonium dioxide, specifically plutonium-238. As the plutonium naturally decays, it releases heat. The RTG uses thermocouples to convert that heat directly into electricity.
So it generates its own power from radioactive decay, no moving parts?
Exactly. It provides a steady, reliable source of electricity and also some waste heat, which is actually useful for keeping the spacecraft's instruments warm in the extreme cold of deep space. RTGs are essential for missions going beyond Jupiter, where solar power just isn't feasible.
And the amount of power it generated was pretty small, wasn't it, considering everything the spacecraft had to do?
Amazingly small. The whole spacecraft was designed to operate on less than 200 watts. That's less power than a couple of standard household light bulbs. It's a real testament to incredible power efficiency and miniaturization in the design. Everything had to be low power.
Keeping it warm must have been just as hard as keeping it powered.
Absolutely. Thermal control was crucial. The main structure is covered in multi-layer insulation blankets, like a high-tech thermos, to trap heat. When it was closer to the sun, they actually had deployable louvers that could open to radiate excess heat away. But out near Pluto, those louvers stay closed, and small electric heaters powered by the RTG keep critical components from freezing. They even painted the interior structure black to help distribute heat evenly through radiation. And of course, everything had to be radiation hardened.
Against cosmic rays and stuff.
Yeah. Deep space is full of high-energy particles. The main computer uses a radiation-hardened processor, a Mongoose V, and there are redundant systems for almost everything: command and data handling, guidance and control, all housed in fielded boxes called integrated electronics modules. It's built like a little tank to survive that long, harsh journey.
And on board, it carried a whole suite of scientific instruments, right? Pluto's eyes, ears, and nose, you could say. What were the key ones?
There were 7 main instruments, a really sophisticated payload. The eyes were definitely LORRI, the Long-Range Reconnaissance Imager. This is basically a powerful telescopic camera, taking high-resolution black and white images. LORRI gave us those first stunningly detailed close-ups of Pluto and Charon, resolving features down to about 50 meters across. Incredible detail.
Okay, LORRI for sharp images. What about color and composition?
That was Ralph.
Yeah.
And yes, like Alice, named after a character from the old TV show The Honeymooners, Ralph was actually two instruments in one. MVIC, the multispectral visible imaging camera, took color images and images in specific near-infrared wavelengths, including one designed to map methane ice. And LISA, the linear Eidolon imaging spectral array, was an infrared spectrometer that mapped the distribution of different ices: nitrogen, methane, carbon monoxide, water ice across the surfaces. It told us what things were made of.
So Lori showed us what it looked like, Ralph showed us what it was made of and its color. What about the atmosphere again, Alice?
Right, Alice, the ultraviolet imaging spectrograph. As we discussed, it analyzed sunlight passing through Pluto's atmosphere to figure out its composition and structure and how quickly it was escaping into space. A crucial piece of the puzzle.
Okay, what else?
REX.
Yeah.
REX, the radio science experiment. This one was clever. It used the spacecraft's main communication system. By sending radio signals from the spacecraft through Pluto's atmosphere back to Earth, scientists could measure how the signals were bent or weakened. That allowed them to calculate the atmospheric pressure and temperature profile very accurately. REX also measured the temperature on Pluto's night side by detecting its faint heat radiation.
Measuring the temperature on the dark side. How?
Essentially by using the big radio dish antenna as a sensitive thermometer to detect the faint microwave energy naturally emitted by the cold surface. Very clever use of the existing hardware.
Wow. Okay, what about particles in space environment, PEP, SII, and SWAP?
Yep. PEPSI, the Pluto Energetic Particle Spectrometer Science Investigation, measured high-energy charged particles around Pluto. This helped understand how the solar wind interacts with Pluto's escaping atmosphere. And SWAP's solar wind around Pluto measured the lower energy particles of the solar wind itself and how Pluto's tenuous ionosphere deflects and interacts with that constant stream of particles from the sun. It's about understanding the whole plasma environment.
And the last one, SDC. Something about students.
That's right. SDC, the Student Dust Counter. This instrument was actually designed and built by students at the University of Colorado Boulder. It measured tiny dust particles hitting the spacecraft throughout its journey.
That's fantastic, giving students hands-on experience on a major NASA mission.
Exactly. It was later renamed the Venetia Burney Student Dust Counter, honoring the girl who named Pluto. A really nice connection. This whole suite of instruments was incredibly capable, power efficient, and miniaturized for its time.
So the mission launches, sets speed records. Walk us through the timeline. When did it actually get to Pluto and do its main job?
Launched in January 2006, incredibly fast. It flew past Jupiter in February 2007, getting a gravity assist, which boosted its speed even more and did some bonus science there. Then came the long cruise across the solar system, mostly in hibernation, to save power and wear and tear on the systems. Years and years of quiet travel. They woke it up for good in December 2014 as it started its final approach phase to Pluto. Instrument checkouts began, anticipation building.
And the flyby itself, the main event.
July 14, 2015. That was the date of closest approach. New Horizons flew just 12,500 kilometers, about 7,800 miles, above Pluto's surface, traveling at over 30,000 miles per hour. It became the very first spacecraft to explore Pluto and its moons up close. And the images and data started streaming back. Well, trickling back, given the distance.
Right. It took a long time to get all the data back.
It did. The last bits of data recorded during that brief, intense flyby didn't finish arriving back on Earth until October 25, 2016, over 15 months later. The bandwidth was low over that huge distance, but it was worth the wait.
But Pluto wasn't the end of the road for New Horizons, was it? It kept going.
Absolutely. That was part of the plan all along, to try and visit another Kuiper Belt object after Pluto, if possible. Mission Control used the remaining fuel to maneuver the spacecraft towards a small KBO called 486958 Arrokoth, which had the temporary nickname Ultima Thule. New Horizons flew past Arrokoth on January 1, 2019. This made it the most distant object ever explored by a spacecraft, over 4 billion miles from Earth. It looked like two pancakes stuck together.
Wow. And it's still going, still sending back data.
It is. It continues its journey out of the solar system. In 2018, its Alice instrument even confirmed the existence of something called the hydrogen wall at the solar system's edge, first hinted at by the Voyager probes decades earlier. New Horizons is still doing valuable science out there in the void.
Navigating something that far away, keeping it on course to hit these tiny targets like Pluto and Arrokoth, and then talking to it across billions of miles, how on earth do they do that so precisely?
It requires incredibly precise navigation techniques. New Horizons was the first mission to use something called onboard regenerative ranging.
Regenerative ranging sounds complicated.
The basic idea is that sending a radio signal out and waiting for the echo gets really hard over vast distances because the signal gets incredibly faint and noisy. Regenerative ranging allows the spacecraft itself to receive the faint, noisy ranging signal from Earth, clean it up electronically onboard, and then transmit a fresh, strong signal back immediately.
Ah, so it boosts and clarifies the signal itself.
Exactly. It gives the navigators back on Earth a much clearer, more accurate lock on the spacecraft's distance, down to less than 10 meters precision, even billions of miles away. It was a huge leap in deep space navigation accuracy.
And communication, getting the data back.
That relied on its large 2.1-meter high-gain antenna dish pointed accurately back towards Earth. It used powerful 12-watt amplifiers called TWTAs to beam the data across space to the huge antennas of NASA's Deep Space Network. It also had smaller backup antennas, just in case. The whole system was designed for reliability over those vast distances, sending data back, albeit slowly, from the edge of the solar system.
And I heard New Horizons carried more than just science instruments. It had some passengers, some mementos.
It did, a really lovely touch, adding a human element to this robotic explorer. Most famously, it carries a small container with some of the ashes of Clyde Tombaugh, Kudo's discoverer.
So he finally got to visit the world he found.
Exactly. A very poignant tribute. It also carries 2 U.S. state quarters, one from Florida, where it launched, and one from Maryland, home of APL, where it was built. There's also a small piece of spaceship on, the first privately built crewed spacecraft, symbolizing future exploration.
And my favorite, the stamp.
Yes, a 1991 U.S. postage stamp that says, Pluto, not yet explored.
Perfect. Talk about fulfilling your destiny.
Couldn't be more appropriate, could it? A wonderful collection of symbolic items heading out towards interstellar space.
Okay, so New Horizons didn't just reveal Pluto, it gave us amazing views of its moons, too. And Pluto has quite a family of moons, doesn't it? Starting with the big one, Charon.
It does. Charon is huge relative to Pluto, almost half its diameter. It was discovered way back on July 7, 1978, by astronomers James Christie and Robert Harrington at the U.S. Naval Observatory. Christie was looking at photographic plates of Pluto, and he noticed they looked weirdly elongated, kind of blurry or lumpy in one direction.
Maybe not just a bad photo.
He suspected not. He dug through older archives and found more images showing the same elongation, and noticed it seemed to cycle over about 6.4 days. He correctly deduced it wasn't an artifact, but a large moon orbiting Pluto with that period, gravitationally blurring the image. Brilliant detective work.
And the name Charon, sticking with the underworld theme.
Yes, Christie proposed Charon, who in Greek mythology is the ferryman who carries souls across the river Styx, or Acheron, into Pluto's realm, the underworld. A perfect mythological link. But there was a personal reason, too. The first 4 letters, C-H-A-R, matched his wife's name, Charlene, so he nicknamed it Charon, partly for her.
That's sweet. And Pluto and Charon have this really weird relationship, right? They're locked facing each other.
They do. It's called mutual tidal locking. Just like Earth's moon always shows the same face to us, Pluto and Charon always show the same face to each other. If you stood on Pluto, Charon would hang fixed in the sky, never rising or setting, just going through phases over that 6.4-day orbital period, and vice versa if you were on Charon. They're locked in this permanent cosmic stare-down.
Wow. So New Horizons studied Charon, too.
Oh yes, big time. Key objectives were mapping its surface composition, which turned out to be mostly water ice, unlike Pluto's nitrogen, characterizing its geology, looking for any trace of atmosphere, didn't find one, and mapping temperatures. Charon turned out to be a fascinating world in its own right, with canyons and mountains.
And then there are the little moons, Styx, Nex, Kerberos, Hydra. They sound like something out of mythology, too. They're behaving strangely.
They are indeed sticking with the underworld naming theme. These 4 are much smaller, discovered by the Hubble Space Telescope between 2005 and 2012, mainly to make sure New Horizons wouldn't run into any unexpected debris near Pluto. And they are weird. They're not round. They're small, elongated, irregular shapes, often described as looking like potatoes or maybe small dumbbells.
But the weirdest part is how they spin.
Exactly. Unlike almost every other moon in the solar system, which rotate predictably, these 4 tumble chaotically. They spin incredibly fast, and their rotation axis wobbles all over the place unpredictably.
Tumbling end over end. Why?
It's thought to be because they're orbiting within the complex, constantly shifting gravitational field created by the Pluto-Charon binary system. They're being tugged on unevenly by both Pluto and Charon as they orbit the system's barycenter, the center of mass, which is actually outside Pluto. This complex pull prevents them from settling into a stable spin.
That's wild. And their orbits are related, too.
Yes, they're all in nearly circular orbits, roughly in the same plane as Charon's orbit, and they're locked in this intricate dance of near resonances. Nix orbits about 4 times for every one, Charon orbit Kerberos about 5 times, Hydra about 6 times. It's like a complex gravitational clockwork.
What does that tell us about how they formed?
This whole setup, the chaotic spins, the resonant orbits, everything orbiting in the same plane, strongly supports the leading theory that the entire Pluto system, Charon, and all the small moons formed from the debris of a single massive collision between a proto-Pluto and another large Kuiper Belt object billions of years ago. These moons are the leftover pieces that coalesced from that impact debris disk.
So the whole system is basically the aftermath of a giant cosmic smash-up.
That's the picture, yes. A really violent beginning leading to this intricate, fascinating system we see today. The dimensions are tiny, too. Nix and Hydra are maybe 50 kilometers across, Kerberos and Styx even smaller, maybe 10-20 kilometers.
Okay, so Pluto is the king, but it's just one example. There are other dwarf planets out there, right? What have we learned about them? Let's start closer to home with Ceres.
Right, Ceres is unique because it's the only dwarf planet in the inner solar system, residing in the main asteroid belt between Mars and Jupiter. It's the largest object in the belt. NASA's Dawn mission orbited Ceres from 2015 to 2018 after visiting the asteroid Vesta. Dawn found amazing things on Ceres.
Like those weird bright spots.
Exactly, especially the super bright spots inside Alcator Crater. They turned out to be salt deposits, mostly sodium carbonate, left behind after salty water from below the surface erupted or sublimated away.
Water from below the surface on an asteroid belt object.
Yes. Evidence suggests Ceres has a significant amount of water ice, possibly even a slushy brine layer or a subsurface ocean beneath its rocky crust. It shows signs of past, maybe even recent geological activity driven by this internal water. It's a surprisingly active little world. There's even talk of a future sample return mission.
Okay, moving further out again. Haumea. What's special there?
Haumea is another Kuiper Belt dwarf planet, and it's notable for being very elongated, spinning incredibly fast. A day is less than 4 hours, and most surprisingly, for having a ring.
A dwarf planet with a ring, like Saturn.
Well, much fainter and smaller, but yes. Discovered in 2017 when Haumea passed in front of a star, it was the first ring found around a trans-Neptunian object. It really shows we shouldn't assume these distant bodies are simple.
Then Makemake. Another key player in the dwarf planet story.
Yes, Makemake is another large KBO, one of the big 4, discovered around the same time with Eris, that forced the planet definition debate. It's very bright, covered in methane ice, possibly ethane and nitrogen ices too, similar to Pluto in some ways.
Does it have an atmosphere like Pluto?
Apparently not, or at least not a significant global one. A stellar occultation in 2011 showed no signs of a substantial atmosphere like Pluto's, maybe a very thin, temporary one when it's closest to the sun. It's named after the creator god of the Rapa Nui people of Easter Island.
And it has a moon.
It does. Discovered by Hubble in 2015, a small, faint moon nicknamed MK2. What's interesting is that the moon is incredibly dark compared to Makemake's bright surface. Maybe it's a captured object, or maybe its weak gravity couldn't hold on to the bright, volatile ices that coat Makemake. JWST recently confirmed methane on Makemake's surface, too.
And Eris, the one that really caused the stir.
Eris, yes. Discovered in 2005, located in the even more distant scattered disk region. Crucially, Eris turned out to be slightly more massive than Pluto, even though it's a bit smaller in diameter. That was really the discovery that made the IAU realize they needed a formal planet definition.
What's Eris like?
Very similar to Pluto in size, and likely composition covered in methane and nitrogen ices. JWST has looked at it too. Some data even hints at the possibility of internal heat, maybe geothermal activity, which is just mind-blowing for something so far from the sun. Could there be a subsurface ocean? Still very speculative, but tantalizing.
And any others worth mentioning? Kuiper?
Kuiper is another large KBO. Interesting because its current shape is quite ellipsoidal, like a squashed ball, which doesn't quite fit with how fast it's currently spinning for it to be in hydrostatic equilibrium.
So it's not perfectly round.
Not quite. The hypothesis is that it used to spin much faster, got squashed into that shape, and then slowed down due to tidal interactions with its moon, Waywat. But it froze in that elongated shape as it cooled, so its shape might be a fossil of its past spin state.
Wow. Like a snapshot of its history.
Exactly. And there are others too. Sedna, with its incredibly distant and eccentric orbit. Gong, Orcus, sometimes called the anti-Pluto because of its similar but opposite orbit. Each one adds another piece to the puzzle of how our solar system formed and evolved way out there in the cold and dark.
Okay, after exploring all these incredible distant worlds through telescopes and robotic probes, the big question inevitably comes up. The ultimate frontier question. Could humans ever actually go there? Could we visit Pluto or Ceres or Makemake? Could we even live there?
It's the dream, isn't it? The ultimate expression of exploration. But the challenges are, well, they're astronomical, quite literally.
Yeah.
We can get a sense of the scale by looking at the difficulties just planning human missions to Mars.
And Mars is practically next door compared to Pluto.
Exactly. Mars is, on average, maybe 140 million miles away. A round-trip mission is estimated to take about 3 years. Pluto is billions of miles away. With current propulsion technology, we're talking decades just for a one-way trip. Decades.
Decades in a spaceship. The isolation alone sounds crushing.
That's a huge factor. The psychological strain of confinement in a small space, so far from Earth for potentially decades, is immense. Crew selection, training for teamwork and conflict resolution, and robust psychological support would be absolutely paramount. Probably more critical than for Mars missions.
And then there's the space environment itself. Radiation must be a killer out there.
It's a major, major hurdle. Unlike Earth, with its protective magnetic field and atmosphere, deep space is awash in high-energy galactic cosmic rays and bursts of solar particles. Dwarf planets like Pluto lack global magnetic fields and have virtually no atmosphere to shield the surface.
So astronauts would be constantly bombarded.
Yes. We can use physical shielding, thick layers of material, maybe water or specialized plastics, but shielding effectively against the most energetic cosmic rays requires a lot of mass. Launching that much mass across billions of miles is incredibly expensive and difficult with current rockets. Ideas like artificial magnetic fields or force fields are still very much science fiction due to the immense power and technology required.
And we've landed rovers on Mars, but landing a whole human habitat.
That's another massive challenge. The techniques we use for robotic missions, parachutes, airbags, even the sky crane that landed Curiosity and Perseverance, which weighed about 1 metric ton, they don't scale up easily.
Why not?
A human Mars mission might need to land 50, maybe 100 metric tons. That's way too heavy for current parachute systems in Mars' thin atmosphere, let alone the near vacuum on an icy dwarf planet. So we need totally new landing tech. We do. There's progress being made, though. NASA tested Loftiide, an inflatable heat shield or aerodynamic decelerator, which worked well in Earth's upper atmosphere. The idea is to create much more drag to slow down heavier payloads. There's also growing optimism about supersonic retropropulsion, basically using powerful rocket engines firing forward to slow the spacecraft down drastically, even at very high speeds within an atmosphere. SpaceX's reusable Falcon 9 boosters have actually provided really valuable data on how this works, showing the rocket exhaust can create a protective bubble against atmospheric buffeting. It's a promising avenue for landing heavy payloads.
Okay, so let's say we solve the travel and landing. What about living on a world like Pluto specifically? The conditions there seem uniquely harsh.
They really are. First, the extreme cold, minus 233 Celsius. Any habitat or spacesuit would need incredibly robust heating and insulation systems, far beyond what's needed for the Moon or Mars. Power requirements for heating alone would be significant.
And the low gravity. You said 115th of Earth's. Sounds fun for jumping, but maybe not great long-term.
Definitely not. We know from astronauts on the ISS that even microgravity causes serious health problems over time. Bone density loss, muscle atrophy, fluid shifts affecting vision. Living long-term in 115th G would likely be even worse than 0G in some ways, as your body might partially adapt but still suffer severe degradation. Bones could become incredibly brittle.
So could we create artificial gravity, like in the movies?
That's likely the only viable solution for long-term health. You'd need large rotating structures, big centrifuges, or spinning donut-shaped habitats, probably built underground for radiation shielding. These would spin to create centrifugal force that mimics gravity for the occupants inside. It's complex engineering, but probably necessary for any permanent settlement.
And the psychological side, again, decades away. Living underground, artificial gravity.
The psychological challenges would be immense. Long-duration missions, even closer to home, show increased risks of depression, sleep disorders, friction between crew members, and sheer monotony. Being billions of miles away, potentially living subsurface with limited contact with Earth, The mental fortitude required would be extraordinary. Designing habitats and mission structures to maintain mental well-being would be just as important as the life support systems.
Wow, it sounds almost impossible. But people still talk about colonizing these worlds. Is that just a sci-fi fantasy, or is there a real rationale behind it? Are they actually colonizable?
Well, despite the challenges, there are compelling reasons why people envision this. From a resource perspective, these icy worlds are incredibly rich. They contain vast amounts of water ice, which can be broken down into hydrogen and oxygen for rocket fuel and breathable air. They also have frozen nitrogen, methane, carbon dioxide volatiles, essential for life support and potentially for industry. Ceres, with its subsurface water, is often highlighted as a potential resource depot or stepping stone to the outer system.
So they're like giant frozen reservoirs of useful stuff.
Exactly. And building underground or subsurface offers natural protection from the extreme temperatures, radiation, and micrometeoroid impacts. That's a common theme in colonization concepts for harsh environments.
But powering all this habitats, mining, manufacturing, the artificial gravity centrifuges, lighting, that would take enormous amounts of energy, right? Way more than an RTG.
Absolutely. For any large-scale self-sustaining settlement, you'd likely need advanced power sources, probably compact fusion reactors. Fission reactors might work initially, but fusion offers the potential for much greater power density with fewer long-term waste issues. That's still a technology we need to fully develop, of course.
So it's tied to future energy breakthroughs, but why do it? Why face all these hurdles? Is it just exploration or something more?
For many proponents, like Stephen Hawking argued, it's about the long-term survival of humanity. Spreading out beyond Earth provides a backup for civilization, a hedge against catastrophes, whether natural, like an asteroid impact, or human-made that could threaten life on our home planet. Establishing self-sufficient colonies elsewhere ensures the continuation of the species.
A cosmic insurance policy.
Kind of, yeah. And looking even further ahead, some envision a future, maybe centuries from now, where if the inner solar system becomes too crowded or dangerous, we could potentially use smaller icy bodies themselves as spacecraft. Haul them out, spin them up for gravity, install fusion drives, and launch them as interstellar arcs or world ships to travel to other star systems.
Yeah.
That's deep sci-fi territory. But it builds on this idea of utilizing the resources of the outer solar system. It's a vision deeply embedded in science fiction, from Clarke to shows like The Expanse, pushing the boundaries of what we think is possible.
Okay, let's try and wrap our heads around all this. From being just a fuzzy little dot in a telescope to getting demoted and then revealing itself as this incredibly vibrant, geologically active world with a whole family of weird moons. Pluto's story is amazing. And it, along with Ceres, Eris, Makemake, all these other dwarf planets, they've completely reshaped how we see the outer solar system, haven't they? It's not just empty space out there.
Not at all. What's truly fascinating, I think, is that these places we once thought were just inert, frozen balls of ice, are now understood as potentially dynamic worlds. They have geology, chemistry, resources. They push the boundaries of where we might find conditions suitable for life, even if it's microbial life in a subsurface ocean. And they really force us to think hard about the future of human expansion. Raises a really interesting question, doesn't it? Is this drive to explore and maybe even colonize these incredibly harsh, distant environments? Is it purely about survival and knowledge? Or is it also tapping into something older, that human impulse for new frontiers, maybe echoing some historical narratives of expansion that we should think critically about?
That's a deep question. So what should you, listening right now, take away from all this? I think it's that the universe is just so much more varied, surprising, and frankly, weirder than we often imagine. Every new mission, every new discovery can totally flip our assumptions on their head. So the next time you happen to look up at the night sky, maybe try to picture those incredibly distant, icy worlds out there. Pluto, Eris, Makemake, silent, holding secrets we're literally just scratching the surface of. And maybe, just maybe, waiting for us.
And perhaps leave you with this thought to ponder. We gain all this incredible knowledge from missions like New Horizons, these deep dives into the unknown. The real question then becomes, what do we do with it? If the value of knowledge is in how we apply it, what path will we choose for these twilight realms? Will our focus be on searching for life, utilizing resources, or ultimately trying to build new homes among the stars? The choices we make now will shape those answers, which are still waiting out there to be discovered.